Alright, well, this is my own little hacking program. It's pretty basic, but it took me like 4 days to figure out, so I hope you enjoy it. So anyways, here's the basic layout of it. I have an integer numeric up and down, which is a maximum of 255 on it. A go button, a write button, a label to give me some information, a list box, and a rich text box. So now here, let me show you what this program looks like. Now, for instance, here I have Spider Solitaire open, and what I want to do is I want to change the number of moves that it saves. So basically, let's do some moves here. Let's say this goes there, this goes there, this goes there, and I want to know more. Okay, so now I got 4 moves done. So the thing I'm going to do first is I'm going to set this to 4, and then I'm going to go down the list of processes that I have open and search for Spider Solitaire, which I always seem to miss the first time around. Let's see, Spider, yep, I missed it. Spider, there it is, it's in Spider Solitaire. Now it's going to go through and it's going to find about 100,000 matches in its memory that equal a value of 4. So now continuing, let's do this, okay, so that makes me moves of 6 now. So now I'm going to change this to 6, I'm going to hit go, and it's going to give me all the values that were 4 that have now changed to 6. So I got about 6 of these guys. Make another move, and that value should change to 7. So of this list here, which of these have changed to 7, we reread them, and there we are, 7. Now just for extra, one more, 9, should have changed to 8, and it did. So there it is, that's the value we're looking for. So now if I wanted to, I can say 0 and hit write. Now notice it didn't change down here, but let me do one more move and you'll notice that bam, moves 1. So essentially I've changed that memory location that Spider Solitaire was using and changed it to 0, and it updated when it had the next move to 1. Now I can also say, instead of 0, I can do 100 and hit write. And then let's see here, what can I move? I'll move this guy there, 101. Awesome. I have now successfully hacked Spider Solitaire. For another example of hacking goodness, here's Notepad, and I'm going to put the character 0 in there. Now, we're dealing with text here, so this is an ASCII thing, and the ASCII value of 0 in byte format is 48, so I'll put 48 in here. And now I gotta search through this list again and find Notepad. Oh, there it is, that was easy. Now it found 26,000 instances of the 48 in the memory for Notepad. So what I'm going to do now is I'm going to change it to 1, which I know is an ASCII 49. Hit go. Oh, well, it already kind of found it. Well, just to make sure, I'm going to put a 2 in there, which is an ASCII 50. Hit go, and there it is. Now I'm going to change this guy to, let's say a 52. That should be 4. So I hit write, and then when I click on Notepad, it updates to 4. Pretty cool. A little hacking program. Now let me go, let's not save this. Let's go through the code here, and I'll show you exactly how this thing's working. First of all, I should note that this is only meant for 64-bit. You can see I've changed my program type platform to 64. I actually have a video on how to do that if you're more curious. I changed 32-bit program to 64. By default, my Visual Studio will make a 32-bit program. So anyways, going through the logic, it's not, or code, it's not too big. Scrolling down, a little more, and that's it. It's pretty small. So the first thing I have to do is import some interop services, and that's just to make our code nicer. And let's see, where do I begin explaining the rest of this code? Well, I'm going to ignore these for the time being. Just keep in mind that there's some stuff there. But what I want to do is kind of go through some memory basics. Now, this kind of is also important for 64-bit, and this is important for 64-bit. These are structures. And the reason I have to define a structure here is because there's no easy .NET structure. Like if you were to go to, say, any other kind of basic structure, like I don't know, dot something. So let's say, I don't know, instance data dot. And of course, that doesn't give me anything either. Of course, why would it, right? Anyways, there's no dot structure for something called memory basic information. So I constructed my own structure, and it's all these things. And it is a type sequential. So as I read in, as I copy all the bytes in, it'll be in this kind of structure with these kinds of data types. And I've made two of these, one for memory basic information and one for something called system info. Now, the next thing that's relatively new, at least to me and probably a lot of you, is enumeration. Enumeration is kind of the same thing, except instead of enumerating like types into a structure, you're enumerating values into a type, if you will. So basically, I'm calling up something called process flags, and if it's process flags or process access flags dot all, that means it is this value, and this is hex. And then I have, query information that is hexadecimal 400. So, anyways, that's some new things. And so let's get into the real code here. After we get past that weird stuff. Oh no, wait, there's more weird stuff. Let's get into the other weird stuff for the time being. First thing we want to do with that is declare some functions. And I have 5 functions here that deal with kernel32.dll. And kernel32.dll is the basic memory access that I need to use to access the memory. Makes sense, right? So anyways, 5 of them here. One is get native system info, and that's actually, you can see down here, it kind of grayed up. It says system info, and this guy really populates the system info structure that I declared up here with the appropriate system information. And I also have read process memory. That's important because I need to find that memory location first based off the values. Write process memory because I intend to write something to it. And then open process to basically kind of get control of the remote process. And virtual query X gets me basically the memory locations that the program's using. Pretty confusing? We're just getting started. Alright, so to the real code then. As you would recognize it, form 1 load, our basic load statement, first grabs all the processes that are currently running, and processes, as you may have seen up here, is a array of processes. And so processes.get processes gets them all. And then for each process in processes, we add a list box item of the process name. So that's pretty easy. Now, once we've clicked on a list box item, here's where the real code starts to take into effect. So first thing we're going to want to do is open the process and really get access to it. So we need to define a new process, hprocesses, and that's defined up here underneath these two guys. So hprocesses is really what we're going to be using for the rest of the program. And what we want to do is say open process with the process access flag of all, because we want to read and write and all that good stuff to it. Then false because we're not inheriting it. This will give you more information here. And then we want the ID of the process we're going to be working with. So it is process of the selected integer .id, selected index. Anyhow, we now defined our H processes. Now we're going to define a few more things here. Bytes to read, that's part of the read process memory. It's not terribly important. Success is a boolean. This is more for kind of debugging your program, and I also use it to say if you got something good, then continue. Data will be where we store all the values that the read returns. Indexes will be the actual address of each byte that I read. And then address is really, I guess, the pointers I'm going through each address that the program's using. And then sysinfo and meminfo are the structures that I predefined. And then tempint is the numeric up-down value. Now, numeric up down dot value is actually as decimal. You can see it right there, as decimal, and that's played havoc with some of my programs in the past. So I usually always convert a numeric up down to an integer first before I use it. So anyhow, we're going to call up that one process that we defined up earlier with the kernel32 get native system info, and we're just going to simply pass system info into sysinfo, the system information. Now the next thing is to put address, which is a long, which in this case is a 64-bit integer, which I think may be unique to 64-bit processors. I guess I have to look at that. Anyhow, we're going to take system info minimum app address, which is one of the items right there, and we're going to dump that into address. And so we're going to start there at address, which is, I guess, the first address that the computer would be using to keep application memory in. And we're going to go using a dual while statement to something. It's 7 FFF because, you know, I felt like it. It's a lot of memory, and usually you never get that far anyhow. So the next thing we're going to do is, let's see here, we're going to actually grab the information of the program at the memory at the address. Are you confused? Because I am. Let's see if I can't talk my way through it. Make some stuff up, see if you believe me. The H process, which we defined earlier, the open process, which gives us access. So we want to read this specific process at this address, and we're going to dump that into memory info for the size of memory info. And if it's happy, then we continue. So basically we have a good working memory info, and so we want to continue with that. Now we're looking for only a certain type of memory, and that would be private memory or image memory, and a state of it's either a comment memory or a reserve memory. And if we have all that, then what we want to do is we want to define an array of bytes for the region size of memory info, and then we want to read the process memory. And since it returns a boolean of successful or not, success is going to equal that, so that we know it worked. But anyhow, this is still going to function as a function. Because, you know, functions. So anyways, H process, so I'm looking at that process, memory info, the base address for that memory chunk, read it into bytes, the array that I just defined, and then memory info for the region size, and then bytes read. Now I never really look at bytes read, it's just there if I ever wanted to see it. It kind of has the same thing as success. If success is false, bytes read will be 0. If it's a true, then bytes read will be more than 0. It's kind of how you can use that if you wanted to. Now, I feel like I should really kind of reinforce how this memory thing works. Think of it as there is at, let's say, the min app address, which is part of system info, holds memory areas, and each memory area is defined for a process, and it has multiple memory areas, so you can kind of think of it as an array. And then we read each memory area, and we throw those into the bytes array that I've made. And then, after that, we go through the bytes array if success. So I equals 0 to bytes length minus 1. And if the bytes data, that is, excuse me, if the bytes data that it returns is temp integer, which is the number we're looking for, then we add that information into data. So we're basically dumping the value into the list of byte. And then we're going to take that index, that memory info address, and we're going to put that into indexes. So basically, here's where it is. This is the, you click on that list box, and it gave me that, whatever, 100,000 addresses that it found. That's right here. That is the indexes. So after all this good stuff has happened, we're going to go to the next chunk of addresses, which is the next memory area, the next memory thing. And that's address equals address plus memory region size, because we're kind of just going to the next region, if you will. Alright, now another thing I should specify is I had this really go nuts on me before, and you really got to be careful about using and editing memory, because I crashed my computer so hard I had to hold the power button for 7 seconds to get it just to shut down. So just a disclaimer, be extremely careful when you're doing memory applications like this. It can be dangerous. So I had my computer crash me twice while trying to make this program. So be careful. And another disclaimer, do what you will with this. I'm not responsible for it. So anyways, there you go. So I put a maximum. If my data gets over 2 million, then, you know, just forget it. We've probably found it by now, whatever we're looking for. So exit the loop. So there we are, exit loop. Now, index list, which is actually defined as a global variable up here. It's a new list of long. And we need to use longs because these addresses are long. They're in the, like, billions, if sometimes. So, for, I guess this could be either data.count or indexes.count. They're kind of just added at the same time. We want to add index to the index list, because indexes is only local to this function is going to disappear as soon as we get out of here. And then, finally, label1.text equals length and data.count, and found is index.count. And really, again, it's going to be the same number. I guess it really never changes, come to think about it. But whatever. So, the next thing is that we click the button. That is, we found our list, we had a length of something, and then we went to our program, changed that something. So now we want to choose the new variable and hit the go button. So upon the go button, which is button 1 in this case, I kind of redefine all the variables that I used before, which is byte thread, success data, new data. That's right, I'd add that. Indexes, tempant for the numeric up and down again, and then bytes of a single byte. So this is only a single byte read. So for I equals 0 to index list, which was populated by all the indexes that we found that equaled our correct value, we want to simply read the memory at that index and dump that into bytes for a length of 1, and then data.add byte 0, so we're dumping the data of bytes back into data, and we're adding indexes into indexed, or the found index from index list. And once we've gone through all those, we want to re-clear index list, because we don't want to reuse the ones we found. We want this to be a brand new list. Now, all of our indexes that are valid are stored here in indexes. So, next thing I'm going to do is I want to say a found compares, which will be our next kind of thing. I guess, thinking about it again, I may not need this because it's the exact same number as would be the index list count. So I guess I don't need this. So, erase. I gotta make this stuff, you know. Oh no, wait, I didn't want that. But I can use something different though. Instead of found list, I can use index list.count. So that way, because I'll get to that. Anyhow, so for the data now that I've retrieved from all my previous index lists, if the data is the new value that I defined in my numeric up and down, then we want to dump the into new data, because we'll be defining that in our rich text box, and then repopulating index list with the appropriate indexes that matched from the previous list. Hope that all makes sense. And now, this is really kind of irrelevant to what the memory thing is, but I'm appending a rich text box here with all the indexes and the data, and I found out that 100,000 things will cause the rich text box to take forever to update. So I really only want to display up to 100. If I have less than 100, then only do it up to index count. And that's about it. So now once I've done this a couple times and found my address, the final thing is button 2 click, which is my right here. I'm going to go, once again, define success. I'm going to define bytes as a single byte, but it has to be an array because it likes arrays. And then temp int, I don't use that here, do I? No. Oh no, I do use that. Because that's the value I'm writing. Good grief. I need some more Mountain Dew. Anyways, I put temp int into the byte and define this, even though it's unnecessary bytes row, and then I do a write process memory of the H processes of the program we were using before of the index list 0, and that's basically going to be the top remaining line here. You only want one left, and I just put 0. I mean, if you want, you could put a list box here and you could select it, and you could say index list of selected value of list box 2 if you want to go like that. But I just did it to the last remaining one of index list. And we want to write bytes. We want to write for the bytes length, which will be 1, and then dumps it into bytes row, which is unnecessary. So there we are. I hope all that was somewhat helpful. I mean, that takes a lot to figure out. So again, be very careful with this, because you can crash your computer easy. Don't do anything malicious with it. Use it for simple stuff like games and whatnot. But I'm just a guy on the internet, and you can do whatever you want with it, I guess. I'm just not responsible. But either way, have fun with that.